So I'll put this up there when we're done, or it'll be on YouTube or something, and I'll link it to Canvas. I haven't quite decided that logistic yet. So the first thing we're going to do is look at points, lines, and planes in Grasshopper. So just the very basic building blocks that we use in Rhino for modeling. So the first thing that we can do is construct a point. So we're going to do a construct point. And it's got this little XYZ icon. And just if you click on that, it's going to drop this component in. The construct point, if you mouse over it, it's going to tell you what it is, what it does, and whether or not it worked. It says this component ran once, it's good. It gave us a point in Grasshopper or in Rhino. Does it look like this, just orange? Then it's just a point. So what she's asking is if it looks like an orange box, does it look like that? Yeah. So if you get that, it's not actually a component. It's not running. It's got a floating parameter, point failed to collect data. It has no input, so it can't output anything. This is a point in Rhino. So if you take this point command or this point component, come over in Rhino and just drop a point in. You can select that point, come back into Grasshopper and right-click to bring up the context menu. If you do that, you've got a couple of options. You can preview, turn it on or off to show or not, choose whether or not the component's enabled, see the warnings, so why it failed. We'll talk about reverse, flat, and graphed later in the course, but what we're really interested in is setting one point, or you can set multiple points. So if you have that point selected, set one point, now it's got a point set to match that one that you had in Rhino. So what I just did, I'm going to Control-Alt-Click and hold on the component. It's going to show me where I got the component from. So it's in the Vector tab, and then it's in the Points component of the Vector tab. Rhino or Grasshopper is kind of finicky. You can't just say point to get the build a point command. You're going to get this data box if you do that. So it's construct point, and then you can choose your XYZ coordinates. So your input here is going to be a set of XYZ coordinates. So to do that, we can use a number slider. Right here, I just searched number. And it's going to default to between 0 and 1. But if you double click on the slider header, it's going to bring up a context queue. It's going to let you choose between floating real numbers, so decimals, integers, even numbers, or odd numbers. And I'm just going to put it on integers, and I'm going to come down here and I'm going to change the max from 1 to, say, 10. That's going to lock it between 0 and 10, where it only encounters the integer numbers. So Grasshopper works by plugging components into one another. You click on the little white dot, you can then click and drag to connect the components to one another. So right now, this base component, you mouse over each of the inputs, it's going to tell you what it's defined as. So one value inherited from one source, it's coming from something outside, set to 0. Locally defined, set to 0, so there's nothing defining it, so it's going to default to a value. If you drag and hold Alt, just like in Rhino, it will copy your component. So I'm just going to go ahead and plug these guys in, and now we've got a point at 0, 0, 0, and we can vary the X, the Y, and the Z components. So we can start to move that point around in 3D space. So now if we wanted to draw a line, who wants to take a guess at how we would do that? Okay. So there are two kinds of lines. There is a line between points. Well, there's a data input line that's going to look like this point did before that we can't use unless we have something in Rhino. But there are two kinds of lines that we'll use. There's a line between 2 points, which is just line. And then there's a line SDL, which is a segment defined by a start point, a tangent, or a direction, and a length. So the line command is going to ask us for 2 points. We only have one. To get around that, we're just going to do a move on that point. So the move component is going to ask you for 2 inputs, a geometry that you're going to move, the G, and a vector of translation, the T. So we don't have a vector right now, but we can fix that. So there are 3 different vectors, x, y, and z. X is traditionally east-west, y is north-south, and z is vertically. In Grasshopper, those are just unit x, unit y, and unit z. So we'll use a unit x, and we'll plug it into this move, and it's going to default to 1. So it's going to move it 1 unit in the x direction, and none in the y and z. So if we plug our point in, it moved it just a tiny bit. We can then use one of these sliders. Again, I'm just alt, click, and drag to copy it. And we can just plug it in, and then we can change how much it moves in any one direction. Now that we've got 2 points, we can use this line between 2 points command. So it's going to ask you for the start point and the end point. So we'll put our point into 1 and then our moved geometry, translated geometry from the move command into the second. Worth noting, you can't select any of the Grasshopper components in Rhino until after you've saved them to Rhino. Grasshopper calls that baking. So if you select your line component, just right-click on it, and you'll have a bake command. It's going to prompt you to choose which layer you want to bake it to. I'm just going to tell it default. Then we're actually going to have a geometry in Rhino that we can use now. That's separate from the Grasshopper definition, so changing that Rhino geometry will not alter your Grasshopper definition. So the line SDL, we're going to do the same thing. Going to give it a start point. See, it's going to default to be in the Z direction, 0, 0, 1. And it's going to default to 1 for the length. And I'm just going to plug this same move in X in. And it's going to ignore that length. It's just going to take the direction, not the distance. Then I'm going to plug that 4 in, and we've drawn the same line now with a different kind of line component. You guys have any questions so far? So right-click on the connection letter. It'll say disconnect, and it'll give you an option of what to disconnect if you have more than one thing plugged into it. So if you want to plug more than one component into a single receiving node, you just hold Shift while you plug it in. Then you can either disconnect all or disconnect a single one, and it'll highlight whichever connection you have selected so you can tell exactly what you're doing. All right, so let's see if we can't turn these lines into a surface. I'm going to do another move command, We're just going to move this line vertically. So I'm going to grab a Z, unit Z, plug that in, and it's going to move it 1 unit up. But to make it a square surface, so let's just plug that 4 in. And you'll see that I'm just plugging those direction, or that length, into the unit vector, and it's changing the length of the unit vector. The default in Grasshopper and in math in general is that a unit vector is 1 unit in length. Grasshopper doesn't have any inherent units. It's going to use whatever your Rhino system is set to. So I have mine in feet right now. But the unit vectors are always going to be in the X, Y, or Z direction and 1 in length unless you effectively multiply it by a different number slider. So now that we've got these 2 lines, I'm going to use a loft command. Just like in Rhino, Grasshopper's loft is going to create a surface through a set of section curves. So we have 2 lines here. Or I should. There we go. We have 2 lines here. One on the bottom and one on the top. So I'm just going to hold shift while I plug these 2 lines into the C component of loft. It's asking for the curves. The O is an option set. Just like in Rhino, you can change the loft between simple, complex. All of the different loft options that we talked about in Rhino can be applied in Grasshopper. So it just created this planar surface vertically lofted between 2 curves. Again, I can select that component, right-click, and then either bake it, or I can turn the preview off. So it still exists, and you can still bake it even though it's turned off in preview. But you won't see it as part of the Grasshopper definition. All right. You guys have any questions about what we just did? So what we'll do is, in this assignment, you're going to need to make some planes between a set of curves. So we're going to go ahead and we're going to just leave this guy here, but I'm going to select everything and turn the preview off. I just selected it all and right-clicked, preview off. So it's still there, it's just not going to load in the Rhino preview. Then I'm going to select it all again and just group it so it's in one place and all locked together. And you can use a scribble, and it's just a little text box. I'm just going to label this lines, or points, lines, and planes. Hit OK, it'll save it. So the next thing we're going to do is talk about how to use a bounding surface, or a set of boundary curves to create a surface. So I'm going to start with a circle. There are a couple of different kinds of circles. You can look at using a circle defined by a center, normal, and a radius, a 3-point circle, circle between 2 tangent curves, a circle between 3 tangent curves. We're just going to go with this center circle. But so you all can see it. I'm curious. In the curves, under primitive geometries, for whatever reason, and then there are a set of circle components. What's up? So I just searched circle, and it is the circle CNR. You can also use the circle, just the plain old circle command, which asks for a base plane and a radius. All right, either one will work. And we can actually do it with both. They're going to ask for very similar things. These two are almost identical. This one's going to ask for a circle with a center point, a normal plane, a normal vector, so a vector that's going to be perpendicular to the plane of the surface, or the circle, and then a radius. This one is just asking for a base plane, and it's going to center it on the origin, and then a radius. So we'll use the circle CNR because we get a little bit more control out of it. But we're still going to leave the normal vector as one of the unit vectors. So we'll use y this time. So I just did unit y. I'm going to plug that in as the normal vector. We're going to use our point from before. So I'm just going to choose this point, bring it down here to be the center. Then we have our little circle. And we can use one of these sliders if we want, so that the radius is variable. In the assignment, when we ask for a variable dimension or a variable option or variable parametric model, we're looking for things where we can change the slider. So we have the circle and we can change the radius. We can move the center point around by moving our point up here. And now we're going to look at a boundary. So the boundary surfaces is going to look for an input of a set of edge curves, either as a single curve or as a collection of curves, which Grasshopper is going to call a list. And it's going to output a surface based on those curves. So it's the equivalent of using a planar surface command in Rhino. We're just going to plug our circle in, and then we have this circular surface, which we can do all kinds of things with. But for now, let's just try and extrude it. So there are a couple of different extrude commands. You can extrude curves and surfaces along a straight path, along a curve, to a point. So you can take a circle and extrude it to a point, you'd get a cone. And you can just do a plain extrude. It's worth noting that unlike in Rhino, Grasshopper does not have an issue with using either surfaces or curves with the extrude command. In Rhino, you have to use extrude surface or extrude curve. They won't work on the wrong geometry. The extrude is going to ask you for a base profile, which we're going to use our surface for, and it's going to ask you for a direction. What we're going to do is we're going to use this y component. We'll give it a distance of 3. So all I'm doing, it's asking me for an extrusion direction. I'm multiplying my unit vector by 3 to get an extrusion length of 3 units in the y direction. Just going to plug it in. It'll extrude it. You can play with this. You can change the extrusion length and drop it down. If it takes it to 0, it's not going to extrude anything. It's going to just remain a surface. Yeah, so I just selected it and then held Alt as I dragged to copy it over. And you can also do like a Control-C, Control-V. And if you have something selected, it won't give you a paste or a copy-paste option in the context menu, so you just have to know that. All right. And a little bit amusing, if you double click on your group background, it's going to change how it wraps to fit the components. You guys follow so far? All right. So very quickly, we're going to go through the basics of lists. Grasshopper is iterative, which means that when you have a list, Grasshopper will iterate through it. So it'll step through it until it comes to the last thing in the longest list. So there are two components that we're going to use for this. Range, which is going to create a range of numbers based on a start and an end point with a consistent set number of steps with a consistent interval between them. And a series command, which is going to give you a list based on a start point, the number of steps, and the step size. So it'll start, if you have it started at 1 with a step size of 1, iterating 10 times, it'll give you a set of 10 numbers beginning with 1 and then adding 1 each time. So we're going to take our base circle from before. Not going to let me hide things nicely. We're going to take our base circle from before, and we're going to use another move command, and we're just going to create a series of moves. So we're going to step it like we will in the assignment to create whether it's a floor height or a set of ribs on a bridge is the assignment for this week. We're going to take the circle and plug it in to the geometry. We're going to just use this y vector as actually better yet, we're going to create a series. So we're going to give it a start point. It's going to default to 0, which is fine. Give it a unit y as the direction. So right now, see what it just did? You've got a series moving in unit y. It's starting at 0 with a step size of 1 and a count of 10. So it's going to iterate through 10 times, starting from 0, moving at 1 unit each time. So we can also use some of these sliders in the N and the C to change the number of steps and the size of the steps. So we've got 4 steps now at a size of 10 units per step. You can start to squish that down or stretch it out however you want or need to for what you're doing. The other way that you can do this is by using the range command. So I just copied that over, and Grasshopper likes to keep things connected when you copy them. It's a little bit frustrating, but that's okay. So we're going to use a range command, and the range is going to ask you for a domain, so a start and an end point, and then the number of steps. The command, or the component to create a domain, is construct domain. And it's going to be this funny looking one that's got a number line highlighted on the icon. The domain data point will not help you here. So the domain key, again, there it is in math on the first tab, is going to ask you for a start point and an end point. So I'm just going to copy these 2 sliders down and use those. When you plug the sliders into a component, they're going to change their in-cap text so it tells you what they are. So these ones say start and end, which gives us a little bit of a hint about what we're doing exactly. So we have our domain. 1 inherited value, 2 to 7, because those are the sliders that I just used. And then the range, or the number of steps, is going to default again to 10. So if we just bring another slider down, we can give ourselves control of that. And now we're going to get a list. So it's going to go from 2 to 7 with 7 steps between. So it's going to give us a total of 8 values with an equal step size between each point. So if we wanted to see that, we can use a panel command. And the panel is just going to be a data dump, kind of. And it's going to let us plug something in, and it's not going to do anything, but it's going to show us what exactly is being output from this component. You can also use a panel to write comments, however you want to do it. You don't have to hit enter or anything. If you hit enter, it's going to put you on a different line instead of actually closing it. So we've got this panel. We know what we're outputting from our range command. And we can put it in to a direction vector and then into our move command. There it is. We've got this set of circles again, just like we did before, and we can squish it down or stretch it out however we want. Begin to create this stacked set using a series or a range command. So similarly, you can use the series and the range to do pretty much whatever you need to. We're going to use them a lot this semester. But we're going to look at scaling like that. So we can use a rectangle command maybe. Every one of these simple geometry commands that I'm using is something that exists in Rhino. So you can do, a box. It's going to give you a bunch of different boxes. Do a polygon, and it'll give you a bunch of different options to make a polygon. So we're just going to grab some sliders. I just copied them that time, Control-C, Control-V. And the rectangle is going to ask you for a base plane, which is going to default to the XY plane, which is fine. See it there? And I'm just going to plug in a couple of values to make a rectangle. And then we can move it just like we did before. I just brought those move components down. I'm going to give it a unit Z because it's perpendicular to Z this time instead of being perpendicular to Y. All right, so we have these rectangles moved. Now what if we want to scale it throughout that iterated move? We want each consecutive step to have a different scale. So what we're going to do is we're going to find the center. So the command we're going to use is polygon center. psyn should bring it up too. Yeah, polygon center. It's going to ask you to input a polygon, which we're going to use these geometries for. It's going to output a set of centers based on the vertices, so the corners, the edge lines, and the average of the centroid, or the area. So it gave us these points in the center of the polygons, and we're going to use those as our base for the scale command. Just a plain old scale, uniform scale. Our geometry is going to be our moved rectangles. our center is going to be the C sub V. And then our scale factor is going to be set up with a series. So we're going to use a series. We're going to give it a number slider. Let's say we don't ever want it to get bigger than what it is at its largest. So we can change where it starts. We can change where it ends, or we can change the number of steps, the step size, I'm sorry. And then we want the number of steps to be, the length of our move list. We don't want to scale more things than we have, and we don't want to scale less things than we have. So what I'm going to do is just a list length. This one right here, it's going to measure the length of a list. So we have a list of geometries with 6 values in it. So it's going to take that base list and output a list as a single number. And we're going to use that length as our number of steps. Then we can plug this series command into the scale factor, the F on the scale component. And so we can see what we're doing. We can hide this base rectangle. And you'll see we've created kind of like a stepped pyramid where we've scaled each rectangle by a different factor. Make sense? So we can do a similar thing with the rotate command. And I'm just going to copy this whole definition down. So now that we have scaled it and we've moved it, we're a little bit less interested in what exactly is going on beyond that we have this stack of rectangles. We don't want to make them different sizes, but we're going to go ahead and rotate each one by a different value. So what we're going to do, use a rotate command, go ahead and drop one in. And that's actually the wrong rotate command. So rotate an object in a plane. So these are both the same quote component. The rotate in a plane is going to default to being in XY instead of being in a YZ. So it's going to ask us for the base plane. You can just take that base plane to be the rectangle that we used, or the base geometry to be our rectangle. The rectangle that we moved. And see, now you've got this rotation. It's going to default to rotating by 1/2 pi, which is 90 degrees in radians. And it's going to default to rotating in XY, which is fine, but we can also use a polygon center again to find the center of our polygons. And we can use that as our base rotation, so it rotates without moving about the center of each polygon. We've rotated everything, but what if we want to rotate them parametrically? Right? So we can use a range command or a series. If you'd rather use a series, they'll both work the same way. And we are going to take our number of the number of moves that we made. So we have 5 here. And we're going to subtract that from 1 so that, again, we're not rotating anything extra. And that's just a subtraction command. And I input A minus B. You can type out subtraction. Difference works. But it'll bring up a fairly self-explanatory panel that says A minus B. It's going to subtract B from A. So we're just going to plug this first one, our number of steps, into the subtraction component. And then I'm going to use a panel and just set it to 1. And then I'm going to plug the panel in. So the panel is now outputting whatever information is in it. As long as you do not hit enter inside the panel, and all it has is a single number or a set of numbers set up x, y, z as a point, it's going to output a data value instead of a string. So we've got our A minus B. We have the result of our subtraction, and we're going to use that as our range step number. Then we're going to say, let's rotate between 0 and 90. We're going to use a panel again. I'm just going to say 0 to 90, and it's going to use that as a range or a domain, in this case, for the range. You can see 0 to 90. Input one value inherited from one source, 0 to 90. Make sure that there's not a space after that in the panel or anything. Gets a little bit finicky. So we've got our range, we've got an output. So let's go ahead and plug that into our angle. But that doesn't look quite right. We should be getting fairly expected numbers because we're assuming degrees, right? Grasshopper doesn't work in degrees. Grasshopper works in radians. So there is a conversion component. If you have something in radians, which is what Grasshopper assumes, you can convert degrees to radians, or you can convert radians to degrees. So you're going to search for whichever your output value is. So in this case, we have radians, we want degrees, so we're going to use a degrees component. Put the radians in, and it's going to give us degrees out. Now we've got a whole different set of values here. See the difference between that in the thousands and then that between 0 and 90? So it looks even stranger. But order of operations, put the radians on this side. A little bit curious. I'll have to look into that. That should have worked. So you can convert the radians to degrees before you put them into the range or after. At this point, we're rotating by degrees, or if we skip it entirely, we're rotating by radians. Either way, you have a variable rotation about the center point of each polygon. And it'll iterate through that. If we come over here and change the size of the rectangle, it'll still rotate. If we change the domain size, the number of steps in it. We change the number of objects that we have. So that is what makes Grasshopper so powerful, that you can go through and change one element and it'll iterate through and update the entire definition. The last thing we're going to talk about before we sign it really fast is the region difference pool. And that's going to effectively act as a Boolean difference that will let you either cut away or break into a different set of shapes where they overlap. So we'll use a rectangle. Build your favorite rectangle. Going to decide right here and now that my favorite rectangle is a 3 by 7 or 3 by 8 rectangle. And then we're going to just go ahead and make a boundary surface using the edges of that rectangle. So we have a plane, and I just hid the rectangle component because I don't want to see this grid and I don't need to see the rectangle edges. We've got the plane now. And we can find our center, so piece in. We can rotate about that center at an angle of, I don't know, let's say 90. So if you just put a number into that search bar, it's going to bring up a number slider that will go up to that number. Just convenient if you don't want to have to go through and open everything. We're going to rotate our surface. So now look, you can change your geometry, but it's in radians. A little bit strange, so I'm just going to convert it to degrees. And now it's a little bit more understandable. So 90 degrees is actually going to rotate it 90 degrees. Should. I'm sorry, it's backwards. We have radians, we want degrees. There you go, now 90 degrees does what you'd expect it to do. So we'll use that, and we will create a region difference. So the component is region difference. And this is just like the Boolean difference. You can see here you've got a trim with region, a region union, region difference, region intersection. So we can look at all of those. They're going to ask for different things. The region union is going to ask for the different curves. And if you turn these guys off, you can see it combines their curves into a single then the region difference. We have our different regions. I'm going to plug one into A, the other into B. I'm going to create a boundary surface based on it. So you can see it cut B out of A. And if we wanted to cut A out of B, then we would just reverse them, plug the rotated one into the A and the base into B, and then create a surface. The same goes for that union command, region union. Got these boundaries. I'm holding shift when I plug it in to get a second component. Boundary. Then the region union creates a surface based on the union of the two things. The intersection does just what you would expect it might. Plug an A in, plug a B in. Going to give you this intersection. Plug it into the boundary surface and you get the intersection of the two surfaces. You can use those commands just like you would the Boolean difference commands in Grasshopper or in Rhino. You guys have any questions? Either about anything we've done today or about the homework. You should have been able to see this week's homework starting yesterday at like noon. So if you've had a chance to look at that and have any questions, go ahead and shoot, otherwise we'll run through it really quickly. All right. I'm just going to bring up Canvas, but this is posted in assignment 2. Make sure that you're uploading a file for your Rhino. So you need a Rhino file, A1 _ last name, Grasshopper file, again, A1 _ last name, and then your lecture questions, which you should be able to submit as a text response, or not a text response, as a comment on your submission, but if you can submit them as a PDF file, again, A1 _ last, or A2 _ last name, rather, then that would be even better. That way I can keep track of it a little bit easier when I'm grading. So assignment 2 is asking you to do a couple of things. It's asking you to model this bridge on the West Thames, and it gives you the different steps that you need to show. So the sectional ribs, the variable number of sides, so you need to have a polygon. I'll just come down here really fast. Polygon, and the polygon is going to ask you to input a base plane, a radius, number of segments, and then a fillet radius if you wanted to fillet the corners, but we don't. So we can just, again, bring our number slider down, radius, number of sides, change the radius, change the number of sides. It's going to fail if you have anything less than 3 sides. So to get around that, we can just set the minimum to 3 here. And again, I just double-clicked on the header of the slider to bring up this Options tab. So you're going to do that, and then got to have variable spacing between sections. So just like we did with that move command, we need to be able to vary that. The length needs to be variable, so you need to be able to vary the number of steps. It should rotate gradually, like we did with that rotate command. Each section or rib should be solid. It shouldn't just be a line. You should be able to vary that width. And then you're going to use those components 1 through 5 to develop a model of a twisting tower. So the bridge is going to move in either the X direction or the Y direction. It's going to be horizontal. The tower is going to ask you to take what you just did with the bridge and bring it upright. So you're going to develop a model of a twisting tower with a similar set of parameters as those listed above. But instead it needs to have variable floor-to-floor heights. So it's going to have planes or extrusions that act as floors with a variable height between and degree of twisting. You need to make sure that the tower has an enclosing surface to represent the skin. That means that you're going to have to use a loft command with the twisted's geometry to begin to wrap that. You're going to submit, like I said, your Rhino model. So it needs to be a Rhino file and a Grasshopper file. That's assuming that you're going to use a point in the Grasshopper or in the Rhino file to anchor. If not, then I won't be upset if you upload a blank Rhino file. But if you upload a Grasshopper file and you don't upload a Rhino file, then I'm not going to be able to see anything if you have a point saved to it, because it's not going to carry the points with it. Lecture questions, Rachel should have gone over those this past Friday. We may actually be 2 lectures behind, so it may be the lecture from 2 Fridays ago that we're answering questions on. I'm not 100% sure. with the holidays, our section is a week and a half behind, technically speaking. But she has gone over them. And then there are a couple of examples down here. The West Thames Bridge, you can see how that might begin to relate to what we did up here with the rotate command. How you might be able to combine those different stacking pieces and then extrude each surface, extrude the curves, and extrude the surface that it creates. Or use, for instance, a set of planes and then a boundary or a region difference, and then extrude the region difference surface. So there are, hundreds of different ways you can go at any one of these assignments. I'm really looking for the endpoint and to see that your logic is sound. If you have a different solution from one of your classmates, that doesn't mean one of you is wrong. So it gives a couple of examples of that. And then here are the examples of what your Grasshopper model might produce. I don't need you to bake this. I just need to see that it works. What we are looking for baked is the tower scheme. That's what I was saying. You can right-click, bake, tell it what layer to bake it on. You can tell it to group them together. It'll bake it, and I told it to bake it as a group, so I've got a group of geometries. So we need to see that you can actually change it. The floor-to-floor height can vary. The building height can vary. The degree of twisting can vary. And the core, that centerpiece in the tower, is there and can vary, either with the same shape as the exterior or a different one. You guys have any questions? So when you submit your Rhino file, it should include a set of models like these ones. They don't have to be exactly like this, but we need to see that you can change all of these different parameters. So this is what should be in your Rhino file. Yeah. In addition to your Grasshopper file. And this is going to be fairly standard. You can see what we did is we just took a screenshot of our Rhino file for this one. But you're going to, on pretty much every assignment we do, upload something in your Rhino file like this. Whether it's a set of steps showing how you got where you did, or a taxonomy set like this where you're showing the different variations you can produce. So we've got about 15 minutes. If you guys have questions, I'm happy to answer them. Otherwise, I'll hang out and you all can start working on this assignment, or you're free to go.